So social media analytics, under the subject we are learning about social network analytics. So let's understand what is this social network analytics. For that we have to understand what is a social network. A social network structure refers to the patterns of relationships and connections among a group of people or organization. How is a certain group connected amongst each other, and what all relationships can be drawn. For example, if there is a person say A, and A is suppose a friend of B, okay, and B has another friend who is C. So this A will also can form a network with C, and in this case B will be a common friend. It will be a common friend. So this A, B, C, they form a group. This group is nothing but a social network structure. Studying social network structure helps us understand how information, resources and support flow within a group, and how this flow impacts the behavior and outcomes of individuals and organizations. So how is the information spreading? For example, suppose B is saying something about this C, that is B's friend, to A. Then A will also understand how C is understanding C. A will send suppose a friend request to C. This way there will be a information which will be shared by B, resources which will be shared by B to A, which will make A understand how this C is. So social network helps in understanding and forming a bigger group, bigger network. So in LinkedIn we send the connections. Why do we send the connection request? So that our network increases, so that we can easily get a job. Why do we have to increase our network? To make more new people, to understand more new people, we increase our network. So social network analysis is a research methodology that uses mathematical and statistical techniques to analyze and visualize social network data. So how is this links? How are the links created? How did C became friend of A also? This is all, this networking and all is done using a mathematical and statistical techniques, which makes us analyze that how people are getting connected with each other. That's why we say that world is a circle. That means you are ought to meet friends which have common friends with you. That's the main reason we say that the world is a circle. So social network analysis is a research methodology that uses mathematical and statistical techniques to analyze and visualize social network data. By studying the social network structure, we can gain insights into the structure and dynamics of social systems and how these systems influence the behavior and outcomes of individuals and organizations within them. So how they will influence the individual and the common group, that is what we understand. What is the purpose of network analysis? Understand overall network structure, example number of nodes, number of links, density, clustering coefficient and diameter. Find influential nodes and their rankings, for example degree, betweenness, closeness, centralities. Find important links and their rankings, for example weight, betweenness and centrality. Find cohesive subgroups, for example pinpointing communities within a network. Investigate multiplexity, for example analyzing comparisons between different link types such as friends versus enemies. So all these things we'll be understanding in the chapter later on. What is a node in a social network media? Social media network, what do you mean by a node? So node is nothing but a individual. For example, if I said A, B, C, these are present A is friends with B, A is friends with C. That's the reason why B and C became friends of each other, because A is the common person who is friends with both, who is friends with B, who is friends with C. So what is node here? Node is nothing but A, B and C are nothing but the nodes. So a node refers to an individual, organization or group that is represented by a point in the network. So these are points. A, B and C are points in a network. A node is connected to other nodes by lines or edges, which relationships or connections between the nodes. So A is friends with B, A is friends with C. That's a link. This is nothing but a edge, or it is a line which is connecting A with C, A with B and B with C. These connections can be based on various factors such as friendships, familial relationships, shared interest or professional communication. Here we have taken the example of friendship, that is A is friends with B, A is friends with C and B and C become friends because of A being their common friend. Next, node in social network. The 5 co-stars of Apollo 13 each is represented as a node in the network. So these are nodes. What are the nodes? Like I said in this part, A, B and C are the nodes. Here you will find these are the co-stars of a movie named Apollo 13 and these are the nodes. And these nodes, they are connected. The actors are connected who are in movies together. They just connect actors who are in movies together. So apart from this Apollo 13 movie, these actors were related with each other in other movies. So these two actors, they never were there in any movie together except Apollo 13. So there is no link which is being formed between both of them. So both of them have only one common movie, and that is what? That is Apollo 13. Ed Harris and Kevin Bacon. Other all actors, they have worked together in other movies apart from Apollo 13. What is an undirected graph? Undirected graph means each end indicates at least one movie that the actors have been together, not including Apollo 13. So these are the names of movies which these actors have been together. And undirected means that they both are there together. So if I say A directed with B, that means A is related to B, but B is not related to A. Here both of them are related to each other. So undirected means that it is a double-sided arrow. Bidirected, undirected and bidirected. So you can understand undirected graph as a bidirectional structure where A to B is also possible and B to A is also possible. Next, a weight graph where weights are indicated both as numbers and by thickness of edge. In this graph, weights indicate how many movies they have been together. So, these two actors have been together in one movie except Apollo 13. This is all in context with Apollo 13 excluded. Here also they have been in one together, one, and these two actors have been together in 4 movies. So the line is darker because it is thickness of the edge, because they have been together in more than one movie. So the connection is very strong. That's why the line is darkened. Directed graphs will have an arrowhead. How do you represent directed graphs? Directed graphs are represented with the help of arrowheads. It can be unidirectional, that is from A to B there is only one directional, or it can be bidirectional, A bidirectional with B. Directed graph, here A to B and A and C is bidirectional. Here A to B, again this is also bidirectional. Only thing is that they have used 2 arrows. This can be represented as this also. So this is nothing but an equivalent structure of this graph. Representing networks, text-based analytics, adjacency list. An adjacency list, also called an edge list. So what is an adjacency list? Adjacency list is also called as an edge list. Each edge in the network is indicated by listing the pair of nodes that are connected. For example, the adjacency list for Apollo 13 network is as follows. So Tom Hanks is going with Bill. So Tom Hanks, comma Bill. Then Tom Hanks, comma Kevin. Tom Hanks, comma Gary. Then Bill, comma Gary. Then Gary, comma Kevin. Gary, comma Ed. This is an adjacency list. If in this adjacency list, if this adjacency list is weighted, if this is weighted graph, then we have to write the weight as well. That is Tom, comma Bill, comma 1. Tom, comma Kevin, comma 1. Tom, comma Gary, comma 4. Then Bill, comma Gary, comma 1. Gary, comma Kevin, comma 1. And Gary, comma Ed, comma 1. So this way we have to specify the weights. These are the weights which are specified. But if the weights are not given, here the weights were not given, so this will be the adjacency list. In case the weights are not given, you just have to write who is going with whom. And here, because the weights were given, we wrote it as comma and the weights are. Adjacency matrix. Here the weight is not given. If the weight is given, then instead of this number 0 and 1, we need to write the weights. But because weights are not given, it will be specified as 0 and 1. Zero and 1. So adjacency matrix, Tom Hanks, comma Bill, there is a arrow. So here in this we'll write a 1. Tom, comma Tom, there is no, so there is, we'll write 0. Then Tom, comma Gary, Tom, comma Gary you have, so we'll write 1. Tom, comma Kevin, there will be a 1. So there will be 3 ones. Then Bill, comma Tom, Bill, comma Tom is present, so 1. Bill, comma Bill, there is nothing. Bill, comma Gary, there is, so 1. Then Bill, comma Kevin, there is nothing, so it will be 0. Bill, comma Ed, there is nothing, so again it will be 0. Gary, comma Tom, Gary, comma Tom you have, so it will be 1. Gary, comma Bill, there is, so it will be 1. Then Gary, comma Gary is 0. Gary, comma Kevin is there, so 1. Gary, comma Ed is also there, so 1. Then Kevin, comma Tom, you have Kevin, comma Tom there is, so here again 1 has come. Then Kevin, comma Bill, there is nothing, so 0. Kevin, comma Gary, there is nothing, so 0. Kevin, comma Kevin, there is nothing. Kevin, comma Tom, Kevin, comma Gary, there is a line, so here it will not be 0. Kevin, comma Gary, this is a mistake, so my bad. Kevin, comma Gary, you will have a 1 because you can see this is the line. Let me use some other marker. This is the line for Kevin, comma Gary. So for Kevin, comma Gary, you have a line, so it will be 1 here. Here you will have a 1, not a 0. Kevin, comma Kevin, there is nothing, and Kevin, comma Ed is also there is nothing. Now Ed, comma Tom, nothing is there. Ed, comma Bill, also nothing is there. There is no edge. Ed, comma Gary, there is an edge which is connecting Ed and Gary, so it will be 1. Ed, comma Kevin, Ed, comma Kevin, there is no edge, and Ed, comma Ed also there is no edge. So this way we have to represent the adjacency matrix. Now adjacency matrix for directed graph. Here there is a directed graph. So how will we write? A, B, C. Here also we'll write A, B, C. A, there is no edge, so 0. A to B there is a edge, so 1. A to C there is a edge, so 1. B to A there is no edge because it is unidirectional only from A to B. So here we'll write again 0. B to B there is no, B to C also there is no. C to A there is because A to C is bidirectional. So here we'll write 1. C to B 0, C to C 0. This way the adjacency matrix will come. Next, adjacency matrix for undirected weight graph. Now this is a weight graph. So we'll write here Tom, Bill, Gary, wait, space is less. Tom, Bill, Gary, Kevin, Ed. Here also Tom, Bill, Gary, Kevin, Ed. Tom to Tom 0. Tom to Bill, here you can see 1, so 1. Tom to Gary, you can see your 4, so 4. Tom to Kevin 1, so 1. Tom to Ed is 0. Then Bill to Tom also 1. Bill to Bill 0. Bill to Gary is again 1. Bill to Kevin there is nothing, so 0. Bill to Ed is nothing, so 0. Gary to Tom you have 4. Gary to Bill you have 1. So this is easy, I guess. This can be managed. I will complete this, but you have to do it on your own. Gary to Gary is 0. Gary to Kevin is 1. Gary to Ed is also 1. Next, Kevin to Tom we have 1. Kevin to Bill we have nothing, so 0. Kevin to Gary we have 1. Then Kevin to Kevin we have nothing, so 0. Kevin to Ed we have nothing, so 0. Then Ed to Tom we have nothing, so 0. Ed to Bill nothing, so 0. Ed to Gary we have 1. Ed to Kevin 0, there is no edge, and Ed to Ed also there is no edge. So this is the adjacency matrix for undirected weight graph. So matrix and list, I hope it is clear. It is quite manageable as well. Next, XML standard format. First we'll write person, then name Tom Hanks, name close. Connections with Tom Hanks are Bill Patrick's. So connection Bill Patrick's, connection close. Connection Gary Sinsay, connection close. Connection Kevin Bacon, connection closer. So we understand that Tom has 3 connections: Bill, Gary, Kevin. That's why we write connection in Bill, Gary and Kevin, and then we close the person. This is the way we'll write the XML. Basic network structure and properties. So subnetwork types, there are 3 types of subnetworks: singleton, dyad and triad. Singleton means only one node is present. This is called as a singleton network when we have only one node present. B and C, there are 2 nodes with one edge. This is called a dyad. And when there are 3 nodes F, D, E which are connected with each other in a form of a triangle structure, it is called as a triad. So this is the subnetworks. There are 3: singleton, dyad and triad. Next, a clique. All nodes in a group are connected to one another. When this happens, it is called a clique. So this is nothing but a triad structure. But it is not necessary that a clique should be a triad. It can be anything. For example, A, B, C, D and this. Here also if you see, all nodes are connected to one another. This can also be called as a click. So for this, all nodes should be connected to one another. That means B should be connected with A, D and C. Likewise, D should be connected with B, C and A. C should be connected with A, B and D. A should be connected with B, C and D. So it should be connected with all the nodes which are present in the network. Here also if you see, D is connected with F and E. E is connected with all the nodes in the network, that is D and F. F is connected with all the nodes in the network, that is D and E. So it should be connected with, one node should be connected with all the nodes in the network. So likewise, all the nodes in the network should be connected with every other node in the network. In simple words, all the nodes in the network should be connected with every other node in the network. That's when you form a click structure. Egocentric network. What is an egocentric network? So if we take this example, then this is 1 degree egocentric network. Why is this 1 degree egocentric network? Let's understand. As we are going one step away from D in the network, this is called as degree 1 egocentric network. It only shows us the nodes D is connected to. So in 1 degree egocentric network, it will only show the nodes which D is connected to. So if suppose this example is taken, then in this D, 1 degree of D is neighbors, immediate neighbors of D, that is A, E, B, Q, C. This is what? This is 1 degree. When I want to talk about 1.5 degree egocentric network, if we want to see only D's neighbors and their connections, it is called as 1.5 degree egocentric network. So that is nothing but, first for 1.5 what we have to do, 1.5 for that first make 1 degree. So this is 1 degree, we know. Now make a 1.5. Now 1.5 will be their connections, that means connections of A, E, B, C and Q. Now from this diagram we can understand that A is connected to E. So here we will draw a connection. A is connected to E. Next, Q is connected to C. So Q and C connected. Then C and B are also connected. So C and B are also connected. Then Q is connected with E also. So Q is connected with E also. So this is what? This is 1.5 degree. That means D, connections of D and their connections internally. So here question arises, will F come because Q is also connected to F? Answer is no. Why no? Because F is not a connection of D. Who are we considering in 1.5? In 1.5 egocentric, we are only considering connections of those nodes who are a connection of D. So what we have to understand, in 1.5 degree, what are we doing? We are considering only those nodes who are connections of D. Very, very important. We are only going to consider connections of D, and in turn we are considering their connections. But which connections? Their connections should not be apart from D. So and their connections means only D's neighbors and their connections. These connections should also be D's connections. Should also be D's connections. You can't say that these are not D's connections. Is it okay? Is it okay to take F? No, it is not okay to take F in 1.5 degree because it is not D's connections. In 2 degree egocentric, F will come. Why? Because now you have to take their connections which are connections of D as well as which are not connections of D. So this is what? This is a 2-degree egocentric network. Here F has P also. So with F you will be connecting P. This is full thing is 1.5. So if I have to draw 1.5 degree 1.5, no, this is whole thing is 2. So if I have to draw a 2 degree is very simple. In 2 degree, the difference is that in 1.5, first understand what is the difference. Okay, first understand difference between 1.5 and 2. In 1.5, whatever connections you are taking, they should have a connection with D. So Q cannot be connected to F in a 1.5. Here Q and F are connected, but you can't show this connection in a 1.5 degree because F is not a connection of D. Okay, but in 2 degree you have to show Q connected with F, because now we are not only considering connections with D, we are considering connections with D, as well as if at all they are not connected with D also, it is okay. So for a 2 degree, let's see the diagram for a 2 degree. For a 2 degree, we will have the whole thing, that is we will have D here, we will have this entire diagram will come, but this F will also be connected to P. So this P is missing over here. Why? Because F is a connection of P, which is not a connection of D. But is it okay? Yes, it is absolutely okay, because here we are considering connections with D as well as not a connection with D. I hope you understand. Here you will not draw this thing. So we will be not drawing this diagram. Only this part we will draw, because we don't have to show its connections. Okay, we have to only show these. So for example, Q is connected with F, F is also connected with P, then E is connected with A, B, C is connected with B, this C is connected with O. Now here we did not show C connected with O. Why? Because O was not connected with D. So in 1.5 we have to just remember one important thing, that whenever we are drawing the connections, we have to ensure that those are connected with D as well. That means those are connected with the node which is given up. Okay, if you see here, if we do O, then it will be a 2 degree. So it will be wrong, because O is not connected to D. C and Q is a connection, is okay. Why? Because C and Q both are connected with D. So you can draw connections which are common connections with D for a 1.5 degree. I hope this is not getting too complicated. Path and connectedness. A path is a series of nodes that can be traversed following edges between them. To determine the length of a path, we count the number of edges in it. The path from M to C has a length of 4. So from M to C, if we see 1, 2, 3, 4. What is this? This is the path length. Path length from M to C equal to 4. How will you traverse? MP, PF, FO, OC. I think this is easy. You have to calculate the path length. The question they can ask you, calculate the path length. Simply you have to calculate the length of the path by counting the number of nodes. So if you count 1, 2, 3, 4, there are 4 nodes. So path length is straight away 4. So just calculate the number of nodes which are there in the path from your initial node to your end node. Next is shortest path. There are 2 shortest paths from node F to E, FAE. So here FAE is our shortest length. Rather than going like this from F to E, we can simply go like this. So this is the shortest path. FBE, again FBE is also a shortest path. Even FQE is also a shortest path. So shortest path will be an important measure to be considered in the network analysis and are sometimes called geodesic distances. So if you want to go from F to E, we will not go from F to O, O to C, C to B, B to E. Rather, we will choose the shortest path because we have to minimize the distance. And shortest path are also called as geodesic distance. So I guess shortest path is also easy to understand. We will always choose the shortest distance, the minimum distance, so that we can save the time. We know that. So from F to E, we will not take a long cut, rather we will take a shortcut. Next is connectedness. Paths are used to determine a graph property called connectedness. Two nodes in a graph are called connected if the path between them in the network. So if there is a path between them in a network, we say that the graphs are connected. An entire graph is called connected if all the pair of nodes are connected, strongly connected graphs. Every vertex is reachable from every other vertex. So every vertex is reachable from every other vertex, then it is called as a strongly connected graph. Examples of strongly connected graphs are cliques. Why it is the best example to give? Because if you have F, you have D, you have E. This is strongly connected. Why it is strongly connected? Because F is a vertex. You can reach F with D also, with E also. So we say every vertex is reachable from every other vertex. If I give this example of A, B, C, D and I join this is also an example of a strongly connected graph, because B can be reachable from A, can be reachable from C, can be reachable from D. Likewise, D can be reachable from B, A, C, C can be reachable from A, B, D. So it is a strongly connected graph. Every vertex is reachable from every other vertex. These are strong examples of cliques. Weakly connected if a path cannot be found between all pairs of nodes using the direction of edge, but paths can be found if the directed edges are treated as undirected, then the graph is called as weakly connected graph. So example of this will be F, then here you will have a D, and say you have a E, and here also you have like this. So this is what? This is a directed graph. If a path cannot be found between all pair of nodes using directions of the edge. So these are the directions of the edge. Here you can see if you want to reach D, you only have a scope of going to E and then reaching to D. From F you cannot reach. So if a path cannot be reached with the help of directions, but if this directed is treated as undirected, so for example, if I am treating this directed as D, F, E, now this directed has become undirected. Now to reach D, we can go from F also, from E also. Initially to reach D, we only took one path, that is we had to go from F to E, then to D. So E was the point through which you could reach to D. From here we can reach from F also to D, and from E also we can reach to D. So what is it saying? This kind of a graph is called as a weakly connected graph. Weakly connected graph means the path cannot be found between all pairs of nodes using the direction of edges. So path from F is not found using directions. But now if I convert this directed graph to an undirected graph, I can easily find the path. That's called a weakly connected graph. Strongly connected is you can find from one node, one node can be reached with help of all other nodes in the network. Weakly connected, one node cannot be reached with the help of all other nodes in the network. In case the graph is a directed graph, if I convert the directed into undirected graph, then I can reach with the help of all other nodes also. This is what it has been said. I think simple and easy. Let's move. Bridges and hubs. Connected components. If a graph is not connected, it may have subgraphs that are connected. These are called as the connected components. 3 connected nodes, a 2 connected component and a singleton. So this was there where we had this example A, then we had this B and C, and we had this D, E, F. These are what? These are nothing but subgraphs. And these subgraphs, so it may have subgraphs. These subgraphs are there. If you take this as an individual component, then these all form the connected components. So this will be an entire graph broken into components. A bridge is an edge that connects two otherwise separate groups of nodes in the network. Formally, a bridge is an edge that, if removed, will increase the number of connected components in a graph. So a bridge is nothing but the edge which we remove, then your number of connected components will increase, because bridge is forming a pathway. So for example, if I have this, if I have this, this, then here B to E, C to D, A to B, A to C, these are all what? These are all my bridges. Okay, this is all my bridges. If I remove these bridges, what I am doing, I am just simply removing these bridges, then my number of connected components will increase. What is happening? I am getting 1, 2, 3 connected components. Initially I was not getting that many connected components. So your bridges is nothing but a link, a connection between the different components. Hub. The term is used to refer to the most connected nodes in the network. Example, node P would be a hub because it has many connections to other nodes. Now, why is this node P? Let's see this example. Node P is a hub. Why is node P a hub? Because it has maximum number of connections. How many? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. It has 9 degrees. That means it has more connections. It has 9 connections, 9 different connections. So it is a point of meeting or a meetup for 9 different nodes. What you can say? You can say that it is a point of meetup for 9 different nodes. That's why it is called as a hub. PF is a bridge. PF is a bridge. If you remove this, then this will be a connected component and this will be a connected component. So bridge, the lesser the bridge is, more the connected components. But now in this diagram we have this bridge, so we have lesser connected components. Rather in this we don't have a connected component, we have only one single connected component because this is a whole single diagram. Thanks to this bridge PF. This is an exercise which can be done. Next we'll start